So today we are talking about improper integrals. And if you look at number one, number one, part D, you can see that we will be doing a definite integral between 1 and infinity. So that's why it's called improper. Infinity isn't really a number, and technically we can't really plug it in. So we'll be dealing with this by using limits. So let's go ahead and just get started and see what's happening. Ultimately, we're trying to answer question 1D. Do you think that the integral between 1 and infinity of 1 over x dx is converging or diverging? If it's converging, then we can actually evaluate the definite integral and get an actual number. If it's diverging, that means the area under the curve between 1 and infinity goes on without bound, and that area is approaching infinity. So first thing that we're going to do is 1a. We're going to use our graphing calculator. Sorry, if you don't have your graphing calculator, pause the video and go grab it. First thing we're going to do is evaluate 1a, the definite integral we have here. So we're just going to use our calculator to do an n-deriv, an f-int, and I'm in the new style here. So I'm starting at 1 and going to 100, and I want to do 1 divided by x dx. And when I evaluate that, I get 4.605, excuse me. In part B, we're going to do the same from 1 to 1,000. So I can just pull back up what I had, and I'm going to go ahead and edit this. It's just not letting me do. Okay, I'll go ahead and redo it. So again, a math 9, f-int, I'm going to go from 1 to 1,000. And again, I have 1 over x. And then that's dx. And when I get that, we're getting 6.907. So we're getting larger, 6.907. So the area could continue to increase with bound, or it could lean off somewhere close to 7 or 10 or something. So the next one we're going to do in the calculator, I'm going to 1. So my definite integral, I'm starting at 1 and I'm going to 1 million. And I'm doing 1 over x again, and dx. And what I get for that should be 13.815. So 13.815. So at this point, I'm not sure if this thing is actually going to converge. It seems that every time I add a couple more zeros to the upper bound, that this thing is continuing to get larger. So if I had to guess right now, I would guess that this is going to diverge. That as I get closer to infinity for my upper bound, this area is going to just get bigger and bigger and bigger and bigger. So number 2, we're doing the same thing. So what I'd like for you to do is pause the video and do 2A, B, C, and D. So please do number 2. Here are the values I got. See, my calculator gave me 0. That's actually here. It doesn't mean anything actually. So if you do it, it makes sense because part A and part B were very close together, and then part C was far away from that. I would back off a couple of zeros until your calculator kind of picked up with you. Part B, I believe this converges, and I'm estimating that it's converging to what we got in part B. If nothing else, you can see that the first 4 decimal places are the same. So I'm confident that as I continue to add zeros, this first 4 decimal places will remain the same. So now we have some information. We have different kinds of improper integrals, and here they are. Number 1, we are going from some constant to infinity. And the way we're going to deal with that is written right here. If we have some constant going to infinity, we're going to take the limit as b approaches infinity when I do my definite integral. So if this thing converges, then we actually get an actual number for that. If it goes towards infinity, then it diverges. Part 2, we have the same idea except that we're going to negative infinity. So again, we have a constant as one bound and negative infinity as the other. We're going to treat it the same way by taking a limit. And again, same deal. If we get a limit value, an actual number, then the integral converges to that number. If it does not and it approaches infinity, the limit, then we know the integral diverges and we cannot evaluate it. Number 3, we have an interesting thing going on that we're going from negative infinity to positive infinity. Then we have this situation. So both the integrals, we're going to have to do 2 limits. So we'd have to do a limit for this one, this first one, and we'd have to do a limit for this one. Both of the limits must exist in order for this kind of integral to converge. So they both must exist, and then you would add the 2 limits together to get what the actual value is. If either one of them is approaching infinity, negative infinity, then this thing is going to diverge. Next page. Let's do some examples. So, example 1. We have exactly what we worked on in number 1. Is the definite integral from 1 to infinity of 1 over x dx. So what I'm going to do is I'm going to use a limit. And I'm going to take the limit as my upper bound, which I'm going to call b for my upper bound, approaches infinity, of the integral from 1 to b, 1 over x dx. So basically what that allows us to do is evaluate this integral, find the antiderivative, plug in our bounds, then I'm going to take. So from here, I need to bring my little limit notation along. I'm still taking the limit as b approaches infinity. And I know the integral of 1 over x dx is the natural log of the absolute value of x. My bounds are from 1 to b. At this point, I can plug in my bounds. I'm still taking the limit. So I have natural log of b. Can we agree that as b approaches infinity, b is going to be positive, so I don't need my absolute value anymore, minus natural log of 1. So I'm taking the limit of natural log b minus natural log 1 as b approaches infinity. So when I plug in infinity, so to speak, I get the natural log of infinity minus 0. Natural log of 1 is 0. So natural log of infinity is approaching infinity, which means this entire thing is approaching infinity, which means my actual integral diverges. We were right in our guess that definite integral in number 1 was going to diverge. To example 2. Example 2 looks a lot like example 1. We have an infinity bound, which means we're going to take a limit. Again, my upper bound is what is infinity, so I'm going to call that b. Integral 1 to b of e to the negative x dx. So I'm going to continue to bring my limit along, and I'm going to take the antiderivative, and the antiderivative of that is negative e to the negative x from 1 to b, and I continue with my limit, and then I plug in my bounds. And when I get here, I don't really follow negative exponents very well, which is going to turn each of these into fractions. And my negative exponent tells me I really have that first term is 1 over e to the b. So my limit continues along. I have a negative 1 over e to the b. The second thing is 1 over e. So let's talk about what's happening here. So for this infinity, I have a negative 1 over e to the infinity plus 1 over e. And e to the infinity is approaching infinity, so I have a negative 1 over infinity, which means I really have that first term is a 0. So I really have 0 plus 1 over e, which means this definite integral is 1 over e. Moving on to example 3. Same thing. So actually what I'd like for you to do, I would like for you to pause the video at this point and do example 3 on your own. Pause the video now, please. So my answer is positive 1/3. And if you have any questions about how I got that, pause the video now to work through my solution. Example 5. 5 has no infinity in it, which kind of makes you go, huh, why is this one thrown in here? I'm just going to draw a quick sketch. I'm going to end up erasing this, so don't draw this right here. If I were to sketch what 1 over x squared looks like, it looks like this. So the integral that we're asked to find is we're finding the definite integral between -3 and +3. So if you can tell, our area is unbounded. It continues on forever as x approaches 0 from both sides, the left and the right, which is why we have a problem. There's a discontinuity at x equals 0, so we have to break this into two limits. I'm going to take one limit, which is going to be this side. So I'm going to have a definite integral from -3 to b, where b is approaching 0 from the negative. Then I have the blue side, which will be the definite integral from a, the limit as a approaches 0 on the positive side, to 3. So this down into two separate integrals. So this might need a little more space. So on the left, we have the integral from 3 up to b of x to the -2 dx plus my other side limit, and now I'm going to take a approaches 0 from the positive of a to +3 of x to the -2 dx. So I've broken this into two separate integrals with two separate limits, and I'm just going to evaluate each one. So for this one, I have my limit as b approaches 0 from the negative, and that is going to be x to the -1 divided by -1 from -3 to b. And then I'm going to add my second limit as a approaches 0 from the positive side of x to the -1 divided by -1 from a to 3. So I'm going to evaluate this. I'm going to plug in my bounds. So now I have the limit as b approaches 0 from the negative, and I'm going to deal with my negative exponent by putting it in the denominator. So I have -1 over b minus -1 over -3. So that's one limit. And then I have plus the limit as a approaches 0 from the positive side, same idea, -1 over 3 minus -1 over a. So let's start evaluating this limit. So at the first limit, my -1 over b is going to become 0, and then this 1/3 is a -1/3. And then in my second limit, the -1/3 will still be there, and the -1 over a as a approaches 0. My 1 over b is actually approaching infinity. This is infinity minus 1/3, and a -1/3 plus infinity. Sorry about that. 1 over 0 approaching. So now I have infinity minus 2/3 plus infinity, which the whole thing is approaching infinity, which means this one diverges. So moving on to example 5. Example 5 is the same as the first style that we did. So example 5 is just going to be the limit as a approaches -infinity, integral of a to 0 of e to the x over 4. So from here, I'm still taking my limit as a approaches -infinity. I have e to the x over 4, so that definite integral, that antiderivative will be e raised to the x over 4. The derivative of the inside is 1/4, which means in my antiderivative, I need to multiply by 1 over 1/4, which is 4. And my bounds are from a to 0. So from here, I'm going to plug in my bounds and evaluate my limit. So I have 4e to the 0, 4e to the a divided by 4. And that's the limit that I'm taking. E to the 0 is just 1, and it doesn't matter that I'm taking the limit there, so that part is just going to be 4. And then when I plug in a negative infinity in my next term, I'm going to get a 4 over e to the infinity over 4. That says infinity over 4. You can't read that. Sorry. Now, e to the infinity over 4 is trying to approach infinity, and 4 over infinity is trying to become 0, which means this definite integral does have a value that converges to 4. Now this next one, I'm going to have to do some work down in example 7, so you might want to have another piece of paper or write really, really tiny, whichever you prefer. This one is actually going to involve integration by parts, so at a glance, no matter what, even if we distribute that e to the negative x, we're going to have an integration by parts. So I'm going to leave it as is since I have that. Anyway, so take my limit, and we're going to do a b approaches infinity, integral 1 to b, 1 minus x, e to the negative x dx. And this is the proper calculus notation, so you actually do have to show me this limit every time, even though I know you can probably work it out without showing it. For the calculus, you actually need to show what this is. So right now, I need the antiderivative. I'm going to quickly do the antiderivative down in example 7. I have an integration by parts. So I have a u and I have a dv. And for my u, it's 1 minus x. And my dv is e to the negative x. So I take the derivative of my u and I get a negative 1. I take that derivative and I get a 0. Pretty happy about that. My dv is going to be negative e to the negative x, and then a negative version of that, which is e to the negative x. I put in my signs, and I'm going to multiply, multiply, and across to the bottom gives me. So fill in what I have, which is negative e to the negative x times 1 minus x. And then I have a positive e to the negative x. My bounds are from 1 to b. So from here, I'm going to plug in my bounds and evaluate my limit. So when I plug in my bounds, I'm going to rewrite my e to the negative x's as 1 over whatever I plug in. So this first thing, and I'm going to distribute at the same time. So I have negative 1 over e to the b, and then I have plus b over e to the b, and then I have a plus 1 over e to the b minus, and then 1 now, negative 1 over e plus over e plus 1 over e. And within each of those, I can cancel a couple out. So this guy and this guy cancel out, and this guy and this guy cancel out. They're all making zeros. So what I'm left with is I have the limit as b approaches infinity of b over e to the b, and then I have minus 1 over e. So at this point, I need to really combine my like terms probably to make a single fraction. So I need on the bottom, I need to multiply the first one by an e over e. So I have e times b minus e all over e. So I have this, I've got b's everywhere. Sorry, I've erased my last step. I don't want to actually make this into two fractions. I want to look at it individually. This into 2 over e is the limit as c approaches infinity 1 over e. And the second term, because there's no b in it, is just going to be 1 over e. Now again, I'm going to continue down into example 7 before I erase everything. So I now have the limit as b approaches infinity. When I try to plug infinity into the first term, I get infinity over infinity, which means I have an indeterminate form, which means I get to use L'Hopital's rule. So my my variable is b, so the derivative of the top is 1. The derivative of the bottom is e to the b, so that's the only limit that I have, and then I'm subtracting 1 over e. So as I plug in infinity here, 1 over infinity, which does indeed go towards 0, which means this value is definitely negative 1 over e. If you need to look at that again, please go ahead and pause the video now because I'm about to erase everything that is within example 7. Okay, so we are on example 7. So we have a function where it's 1 over 1 plus x squared. And I'm going to take a quick look at that. So my y equals, I'm going to put 1 divided by 1 plus x squared. And I think I have a standard window. And let's see what that looks like. Okay, so we have just this basic thing that's symmetric about the y-axis. So in this problem, we are looking at the region in the first and second quadrants. Between the graph of f and the x-axis. So I would need to know where it is equal to, sorry, it never actually touches the x-axis. It goes on forever and ever. Let me put the picture back up. If I do a zoom in and you look closely, what's happening is the x-axis is an asymptote, and it's an asymptote that never crosses the curve. So this area is unbounded. So it's going to go on forever in the right and left directions because the curve never touches the x-axis. So what that means is we are trying to take the integral from negative infinity to positive infinity of 1 over 1 plus x squared dx. So that's the integral we are trying to find. Now that makes me have two limits, which I'm not really happy about, but because this was symmetric about the y-axis, what I can do is do 2 times the definite integral from 0 to positive infinity of 1 over 1 plus. So that's the route I'm going to take. I'm just going to double this definite integral. Now to do that, I still have to take a limit, and it's my upper bound that's going to go towards infinity. So I'm going from 0 to b of 1 over 1 plus x squared dx. And I'm just so happy to see this blast from the past. This definite integral, 1 over 1 plus x squared, we should know that antiderivative. It is an inverse trig antiderivative, and it is tangent inverse. So that is going to be 2 times my limit as b approaches infinity of tangent inverse b minus tangent inverse of 0. So what that's saying is my angle is going, for the first one, the first term, tangent inverse of b, my angle is trying to approach infinity. Sorry, the tangent is trying to approach infinity. What is my angle trying to be? And I don't know if you remember what the graph of tangent looks like. Quick sketch of tangent. Tangent looks like this, and it repeats itself. And this little asymptote is pi over 2. So as my tangent's going towards infinity, which is up here, the x value, essentially, because I'm doing an inverse tangent, is trying to approach pi over 2. So I have pi over 2 minus the tangent inverse of 0. The x value is trying to approach 0, so that's going to end up being pi over 2 times 2 pi. So for example 8, we again have an unbounded region in the first quadrant between the graph of f and the x-axis. So we're in the first quadrant. We have a domain of 0 to infinity, so what we're looking for is the definite integral from 0 to infinity of e to the negative 2x dx. Actually, volume, I apologize, volume between 0 and infinity. We're taking this revolved the x-axis. So if I'm revolving that about the x-axis, that means I'm going to have pi times my radius, which is going to be this, times my thickness, which is going to be that. So my radius has to be squared. So I'm going to take a limit here, which is infinity, 0 to b. I'm going to pull the pi all the way out, sorry, in front of my limit. I now have e to the negative 2x squared, e to the negative 4x. And then I'm going to take the anti-derivative, 4x times negative 1 over 4. And I'm going to plug in my bounds, and I'm going to write that in, not in calculus speak, but in algebra speak. So my e to the negative 4x, I'm going to put in the denominator. So I have negative 1 over 4e to the 4b minus negative 1 over 4e to the 0. And when I evaluate that limit, that first term is trying to become 0, and that second term is trying to become a positive 1/4, which means we end up with pi over. So that is day 1 of improper integrals. This is the end of this video. There is a second video on improper integrals, and feel free to end this video and start watching the next one. I hope you have a nice evening if this is your last video for today. Otherwise, continue with your day.